Now we're going to start to look at how we can integrate what are called rational functions. We saw rational functions earlier when we talked about functions which are polynomials divided by other polynomials. And one way we can deal with that is to look at polynomial division. So you might remember long division of numbers. So doing things like trying to figure out 60 divided by 5. And we might look at doing something that looked a bit like this. Put the 60 inside a square and the 5 outside. And say, how many times does 5 go into 6? Well, it goes in once. But there's one left over. How did we get that one left over? Another way to do it is to go like this. 1 times 5 is 5. We've still got a 0 there. 60 minus 50 is 10. And there's that one left over that we have. So then we'd say, how many times does 5 go into 1? Well, it doesn't. 5 does go into 10 though, and it goes in twice. So we pop a 2 up here. 5 by 2 then is 10. We subtract those and we're left with 0. So we'd say that 60 divided by 5 is equal to 12 with 0 remainder, or just straight up 12. So that was long division. What we're going to see now is we can do that for polynomials as well. It's slightly different, but it's pretty much the same thing. We can also do it for lots of different functions raised to different powers. It's called algebraic division. You can do it for exponentials or other functions as well. So let's look at a little terminology. Improper rational functions. Those are rational functions that have their numerator with a higher degree than the denominator, like x cubed divided by x squared. 3 is bigger than 2. A proper rational function, on the other hand, has a numerator with a lower degree than the denominator, so something like 1 on x to the 4. Now we can use polynomial division, or dividing polynomials in this long division kind of way, to rewrite improper rational functions as the sum of a polynomial and a rational proper rational function. Once we've got things like that, we know how to integrate polynomials. Some proper rational functions we can integrate as well. So what we can do is find a way to integrate the original function, which may have been an improper rational, using things that we already know about. So let's have a look at how this works, this polynomial division thing. Here's one that we can actually just do. We know that we can cancel x cubed on x to get x squared. So let's make sure that our method for polynomial division gives us the right answer here. So remember, what we want to do is, just to use my numerical example first of all, 5 into 60. 5 goes into 6 once, so then we say 1 times 5 is 5. Subtract the two numbers, 6 minus 5 is 1. Carry our 0 down and we've got 10. 5 doesn't go into 1, so we have to look at the whole thing. 5 goes into 10 twice, so we pop a 2 up here. 2 times 5 is 10. Subtracting those, we end up with 0. So we know that 60 divided by 5 is going to be 12 with no remainder. So what we're going to do now is say the same sort of thing, but with x going into x cubed. So then we've got to say, how many times does x go into x cubed? Well, or what's left if we have that? We've got x squared. So in other words, x squared times x is x cubed. Subtract those two, and of course we find that we've got 0x cubed left over, or in other words 0 remainder. So x cubed on x is equal to just the thing up the top there, x squared. So this one looks like it's going to work out. But what about if things get a little bit more complicated? Something like this one, x cubed plus 1 over x minus 1. Let's try to write that as a polynomial and a proper fraction. So I'm going to work the same way. X minus 1, I'm going to try to squeeze that into x cubed plus 1. But I want to make sure that I've got all of the possibilities here. So there's some x squareds and x's missing in there because I've got 0 coefficients. So I'm going to leave space for them. It's kind of like keeping your houses straight, like you did with plain numbers back when you were in primary school. So 0x squared plus 0x, and then plus 1. Now I don't try to squeeze the whole thing in there. All I have to worry about is the biggest power of x. So I'm going to say, what times x gives me x cubed? Well, it's x squared. X squared times x gives me x cubed. X squared times minus 1 is going to give me minus x squared. So then I subtract those away. X cubed minus x cubed, of course, goes away. That's exactly what I wanted. 0x squared take minus x squared is x squared. And I just bring these ones down, and they become the new piece that I'm working on. So plus 0x plus 1. Now I've got what times x is x squared? Well, it's just x. So x times x is x squared. X times minus 1 is minus x. And I subtract those away, I've got gone, x plus 1. What times x is x? 1 times x is x. So 1 times x, and then minus 1. So we're left off down the bottom here. When we subtract those two, we're going to have 1 minus minus 1 is 2. So in this case, we've actually got a remainder that we've got to deal with. So how are we going to deal with that? Well, basically what we're saying is x cubed plus 1 divided by x minus 1 is equal to this polynomial up the top plus a remainder, plus 2 on x minus 1. So there's still 2 on x minus 1 left that we can't get rid of. So that's how we write it. So we're going to have x plus 1, x cubed plus 1 over x minus 1 is the polynomial result, x squared plus x plus 1. And then plus our remainder, 2 over x minus 1, which is, or should be, and is, a rational function, but a proper rational function. 2 is a lower power of x than x. So we've ended up writing our weird looking improper rational function as a polynomial piece, x squared plus x plus 1, and a proper rational function. Now imagine for a moment that we were trying to integrate this piece. I don't know how to integrate that, but I do know how to integrate polynomials, and I even know how to integrate this because that's just going to be a natural log sort of function. So that's great, we've turned it into a kind of function that we can integrate just by using this polynomial division thing. And that's exactly what the next question asks us to do. So find the integral of x cubed plus 1 over x minus 1. Because we've just polynomial divided, we know that that's then the integral of x squared plus x plus 1 plus 2 over x minus 1 dx. And then we can just use our rules. The integral of x squared is going to be x cubed on 3. The integral of x is x squared on 2. The integral of 1 is x. Now the integral of 2 over x minus 1, that's going to be that 2 comes out as a constant multiplier, and the log of x minus 1. And don't forget your plus c. So, done a little bit of polynomial division and shown that we can now integrate some of these improper rational functions by first dividing them and writing them as a polynomial and a proper rational function. So that's kind of the idea behind the polynomial division. And don't forget, you can use it for other functions too. So things like functions like e to the 2x, e to the x, e to the 3x. You could do polynomial, or not polynomial, but algebraic divisions on those as well. It might be something interesting to check out. So if you're looking in any textbooks, check out sections on polynomial division and also integration of rational functions, and attempt any of the exercises that you want to check out on the Blackboard site.